Hello, good afternoon. My name is Philip. I'm here to make a short presentation for students preparing for their level 3 physics exams. We'll go through this revision, and by the end, I hope you're able to solve your physics exams more easily. It's very hot. I have my water here. Thank you. So you are welcome to this revision session designed to help students preparing for their level 3 physics exam. Today we will explore the fascinating world of waves and optics, breaking down complex concepts into manageable chunks and providing you with practical problem solving techniques to help you prepare for your upcoming exams. Waves form through different processes that impact how they develop. One main way is through friction when wind blows across water. This friction creates ripples and bigger waves by transferring energy from the air into water. Tides also contribute to wave movement. They are caused by the moon gravity and to a lesser extent the sun's gravity. This gravitational force leads to the regular rising and falling of ocean waters, showing how water interacts with celestial bodies. Phase difference is an important idea in understanding waves. It refers to difference in position between wave cycles. In transverse waves, in phase means 2 points along the waves are at the same level. So both the high point, that is the crest, and the lower point, trough, align. This alignment leads to constructive interference, where waves combined effectively to create higher waves. On the other hand, out of phase means 2 points at different level, which can cause destructive interference that lowers the wave intensity. Similarly, longitudinal waves, which have compressions and refractions, phase difference also matters. In phase occurs when 2 points sinus up during the compression and refraction cycle, meaning they experience maximum compressions or maximum refractions at the same time. This connection boosts wave energy. However, out of phase point happens when one point is at maximum compression while the other is at maximum refraction, which leads to destructive interference and less energy in wave. So the phase difference between points in a wave cycle significantly impacts wave behavior and energy transfer. For longitudinal wave, the oscillations move parallel to the direction of the wave, highlighting the connection between the compression and the refraction. This setup improves energy transfer in the wave and illustrates the complex relation between wave properties and how they move through different material. Understanding this concept also helps clarify the nature of waves, which is important in the fields such as oceanography, acoustics, and so on. Wave can be mechanical, requiring a medium such as sound wave traveling through air, or electromagnetic waves, which can pass through a vacuum like light. The frequency is the rate at which wave pass a point within a unit of a time. Is measured in hertz. The time period can be calculated using the formula time equals to 1 over frequency. The speed of wave can be determined using the formula v, that is velocity equals to frequency times lambda. This fundamental concept can be used to understand wave-related problems effectively. In wave, particles move in different ways depending on the type of waves and this movement significantly influence their characteristics and behaviors. Furthermore, mechanical waves require a medium such as air, water, or solid to travel through. This requirement means they cannot propagate through a vacuum. Sound wave and water wave fall into this category as they rely on particles in their respective medium to carry wave energy. In contrast, electromagnetic waves are unique because they do not require a medium to travel. They can move through the vacuum of space, allowing them to transmit energy across the vast distance. Light waves and radio waves are prime example of electromagnetic wave. They move through empty space at the speed of light, making them essential for various technologies, including communication, heating, and so on. Water wave has a wavelength. Let's do a small calculation here. I couldn't put that on the space because of time. So just have a piece of paper and a pen. Let's do calculation together. A water wave has a wavelength of 2.5 meters and frequency of 0.8 hertz. Now it says calculate the speed. To solve the problem, we need to use a formula for wave speed and time period. So a time period using the formula, that is v, velocity equals to frequency times lambda. So given that the wavelength is 2.5, frequency is 0.8 hertz. Now substituting the values into the formula, we get 0.8 times 2.5, which is equals to 2.0 meter per second. I think you got it. That's good. So we can see it's very easy. So the wave speed is 2.50 meter per second. To calculate the time, using the formula T equals to 1 over frequency, as I said. So frequency 0.8, substitute the equation is 1 over 0.8, which is 1.25 seconds. That's the time period, is 1.25 seconds. Simple optic provides elaborative evaluation of the reflection and refraction that involve bunching back and bending of light across different media. The mirror and lens play an important role in depiction of the concept since they have the best platform for the processing. Reflection occurs when light bunch back off the mirror. Mirrors initiate the reflection process by causing the light incidence rays to bunch back of the mirror. Mirrors also play a key role in the reflection process by providing an elaborative, smooth landing site for light. The site redirects the light, improving the overall reflection mechanism. Refraction is the bending mechanism initiated by light as it travels different media. The concave and the convergence lens elaborates the light movement mechanism, determine the refraction rate. Concave have a thinner middle part that spread light from the focal center. So understanding simple optic offers a comprehensive understanding of reflection and refraction. Sorry, let me just skip this one. Yeah. Snell's law provides a clear illustration of how light bends as it travels between different media. Offering a detailed understanding of the angle of incidence. The discussions extends to important phenomena such as total internal reflection and polarization, which occurs when light follows a defined path, allowing it to concentrate on specific point. The law can be mathematically expressed with the formula n sin theta. To determine the angle of reflection effectively, the process involves three main steps. Number one, identify the refraction index. This is crucial parameter that defines how much light bends when entering a medium. Second, measure the angle of incidence. This is the angle at which the incoming light ray strikes the boundary between two different media. Three, apply Snell's law. It said utilizes the values obtained to calculate the angle of refraction or reflection as detected by the law. So let's give another example here. You can take a pen and sheet of paper. You can work it together. A light ray travel in air a light ray travel in the air, that is the n equals to 1, enters a glass block that's n equals to 2 at the angle of incidence of 45. It said find the angle of refraction. We can use the Snell's law to calculate this. So given the information, the refraction index of air is 1. The refraction index of the glass, that's the N2, is 2.0. The angle of incidence equals to theta, which is 45 degrees. Then step 2, substituting the values into the Snell's law. So after that, then we rearrange the equation. We can rearrange the equation to solve the angle of refraction, which is equals to sin theta 45 degrees, which is 2.0. Now, after that, we can use to calculate the value. Now, the value of sin 45, which is approximately 0.707. That it is 0.707 divided by 2, which gives us 0.3535. So, using the inverse sin function which you have on our calculator, now we can find the angle of refraction by using the inverse sign, which gives us, so the angle of refraction is approximately 20.7 degrees. 20.7 degrees. Total internal reflection is a phenomenon where light travels through a material but reflects back when it approaches the boundary of a medium. This often occurs at angles greater than the critical angle, resulting in the light being completely reflected within the original medium. On the other hand, polarization is the process that enables light waves to oscillate in a single plane, restricting their direction and thus eliminating the confusion that can occur in multiple wave oscillation. This characteristic is particularly valuable in reducing glare and enhance contrast in various optical applications. The diagram and accompanying table offer a comprehensive analysis and representation of electromagnetic rays and their corresponding wavelength. The table highlights current application across various sectors, particularly in electronics and medicine. Gamma rays, for example, have a high frequency rate and primarily is utilized in cancer treatment, where they target and destroy malign cells within the body. Time will not allow me to go through each one of them, but as you can see from the screen, you can see how the basic properties and how they are applied. So let me move to the next slide. Diffraction and interference are wave phenomena where diffraction involves the spreading of waves as they pass around obstacles or through opening, while interference refers to how overlapping waves combine to form patterns of destructive and constructive interference. Diffraction transverse waves in diffraction, transverse waves occur when waves like light encounter obstacles or slits comparable to their wavelength, causing bending or spreading. Longitudinal wave, sound waves also experience diffraction, allowing sound to bend around corners. Single slit diffraction, wave passing through a narrow slit spread out with more significant diffraction occurring at slit. Please, because of time, I'm conscious of time. Interference. Two-source interference require two coherent sources of wave that can overlap, leading to patterns where constructive interference creates bright areas and destructive interference results in dark areas. Young double slit experiment demonstrates interference with light passing through two narrow slits, creating an alternating brighten and dark pattern. Data analysis. Single slits diffraction. In single slit diffraction experiment, the angle of the first medium is related to the wavelength. Slit wavelength, slit wide, and distance to the screen using the formula which is called theta equals to lambda times A. In diffraction creating, the path difference between adjacent slits determine the maxima observed. Analyzing diffraction data involve measuring fringes position, calculating fringes space, and apply relevant formula to determine wavelength. Now, I will end here. Please, if anyone has a question, you can ask. Thank you very much.